this module, you will learn about transformers. A transformer is a device used to increase or decrease the voltage of an alternating current. It is used in power transmission to reduce the power losses and to increase the efficiency of power supply. Transformers work on the principle of mutual induction. According to the principle of mutual induction, when two coils are placed close to each other and if one of the coil carries a time-varying current, a current is induced in the other coil. A transformer comprises of two coils, C1 and C2, insulated from each other. These coils are wound over a soft iron core. The soft iron core is provided to increase the magnetic flux through the coils and to provide a medium through which all the magnetic flux through the primary coil also passes through the secondary coil. This increases the mutual inductance of the two coils as more flux from the first coil now passes through the second coil. If the time-varying magnetic flux produced by coil C1 passes through the other coil C2, an EMF E is induced in coil C2. The EMF induced in the coil C2 is equal to minus M dI by dt, where dI by dt is the rate of change of current in the coil C1 and M is the mutual inductance of the coils. The negative sign here indicates the direction in accordance with Lenz's law. The coil C1, at which input voltage is applied, is called the primary coil, and the coil C2, at which output voltage is obtained, is called the secondary coil. Let the number of turns in these coils be NP and NS respectively. Let us consider the case of an ideal transformer where the primary coil has negligible resistance and all the magnetic flux in the core links both the primary and the secondary windings. In such a case, the energy in the transformer and the core are zero. Then, due to mutual induction, the induced EMF or voltage in the secondary coil ES is directly proportional to the number of turns NS in it. Then, according to the principle of mutual induction, the EMF ES is equal to minus NS into d phi by dt, where d phi by dt is the rate of change of the magnetic flux linked with the secondary coil. The minus sign is in accordance with Lenz's law. The alternating flux phi also induces an EMF referred to as the back EMF in the primary coil due to self-induction. This EMF EP is proportional to the number of the turns NP in the primary coil. This back EMF EP is equal to minus NP into d phi by dt, where d phi by dt is the rate of change of the magnetic flux linked with the primary coil. The minus sign is in accordance with Lenz's law. For an ideal transformer, the primary coil has zero or negligible resistance. Therefore, the induced EMF EP is equal to the voltage across the primary VP. Hence, we get VP is equal to minus NP into d phi by dt. Let this be equation 1. If the current taken from the secondary coil is small, as it is an open circuit, then, to a good approximation, we get induced EMF ES equal to voltage across the secondary coil Vs. Hence, we have Vs is equal to minus Ns into d phi by dt. Let this be equation 2. Dividing equation 2 by 1, and simplifying. We get Vs by Vp equal to Ns by Np. Let this be equation 3. Thus, we observe that the ratio of the voltage across the secondary coil to that across the primary coil of a transformer is the same as the ratio of the number of turns in the secondary coil to that in the primary coil, respectively. Assuming the transformer to be 100% efficient, that is, there are no energy losses, then the input power is equal to the output power. This is a good approximation since a well-designed transformer may have an efficiency of more than 95%. 100% efficiency is not practically possible because of various losses. We know that power P is the product of the current I and the voltage V. Hence, we get P is equal to IV. Now, for an ideal transformer, we have power in the primary coil, PP, is equal to power in the secondary coil, PS. Let this be equation 4. This can be written as IP into VP is equal to IS into VS. Or Vs by Vp is equal to IP by IS. Let this be equation 5. From equations 3 and 5, we get Vs by Vp is equal to IP by IS is equal to Ns by Np. Let this be equation 6. This shows that the current in the coils is inversely proportional to the number of turns in the coil. Since I and V both oscillate with the same frequency as the AC source, equation 6 also gives the ratio of the amplitudes or RMS values of the corresponding quantities. Now, we can write the voltage and current in the secondary coil in terms of the voltage and current in the primary coil as shown. Let these be equations 7 and 8 respectively. If the secondary coil has a greater number of turns than the primary, the voltage is stepped up. That is, output voltage is higher than the input voltage. This type of transformer is called a step-up transformer. In this type of a transformer, there is less current in the secondary coil than in the primary coil. For example, if the primary coil of a transformer has 100 turns and the secondary has 200 turns, Ns by Np is equal to 2 and Np by Ns is equal to half. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 440 volt. In other words, it is stepped up to 440 volt output at a current Is equal to 5 ampere. Conversely, if the secondary coil has lesser turns than the primary coil, the transformer is called a step-down transformer. Output voltage is lesser than the input voltage. That is, the voltage is stepped down or reduced and the current is increased. For example, if the primary coil of a transformer has 200 turns and the secondary has 100 turns, Ns by Np is equal to half and Np by Ns is equal to 2. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 110 volt. That is, a step down to 110 volt output at a current Is equal to 20 ampere. These equations apply only to ideal transformers, as we assumed. However, in practical situations, all transformers incur small energy losses due to various factors, such as flux leakage, resistance of winding wires, eddy currents, and hysteresis. Flux leakage can never be completely eliminated, as not all the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. To minimize the flux leakage, the primary and the secondary coils are wound one over the other. As the wires used for the windings have some internal resistance, some energy is lost due to heat produced in the wire whenever a current passes through them. In high current, low voltage windings, this loss can be minimized by using thick wires. Due to changing magnetic flux in conductors, induced currents known as eddy currents are produced in them. The alternating magnetic flux induces eddy currents in the iron core. The eddy current in these closed loops results in generation of heat and loss of energy. This effect can be reduced by having a laminated core. The alternating magnetic field repeatedly results in the reversal of the magnetization of the core, which consumes some energy due to heating of the core. This is called hysteresis loss. This loss can be minimized by using a magnetic material which has a low hysteresis loss. For transmitting electricity over long distances, we use transformers. First, we use a step-up transformer to increase the voltage and consequently decrease the current in the transmission lines. This reduces the loss of energy as heat. Voltages are then stepped down at various substations and utility poles before it reaches our homes in the range of 220 to 240 volt. There is a practical upper limit to the voltages we can use for transmitting the electrical energy through the transmission lines. Excessive voltages can ionize the air around the transmission lines. This in turn can create a conducting path to the ground or other objects near it, and also can possibly cause damage to life and property in its vicinity. Hence, long strings of insulators are used to keep the transmission lines away from the towers supporting them, and insulators are also used to maintain separation between the wires. You have now reached the end of this module. In this module, you have learned that a transformer is a device used to increase or decrease the voltage of an alternating current. Transformers work on the principle of mutual induction. According to the principle of mutual induction, when two coils are placed close to each other and if one of the coils carries a time-varying current, a current is induced in the other coil. For an ideal transformer, the ratio of output voltage to input voltage is equal to the ratio of input current to output current, which is equal to the ratio of number of turns in secondary coil to that in primary coil. If the secondary coil has a greater number of turns than the primary, the transformer is called a step-up transformer. If the secondary coil has a lesser number of turns than the primary, the transformer is called a step-down transformer.